And the goal of the lab was to observe the system and use a computer model to predict the observed motion using Newton's second law and the energy principle. And the model that was generated accurately predicted the motion. In Tracker, the origin was placed at the top of the spring, and the mass was calibrated to be 0.7 meters. And this is the negative y direction and the positive x direction. And the data was gathered, and this x and y position was then copied and pasted into an Excel file and stored to be later inputted into the model for comparison. Alright, initial information was gathered from the observed motion to be placed into the model. And in the model, this is where the mass is inserted, the initial position, initial velocity. And also, the constant g was defined, and the stiffness of the spring was defined right here, which is found over here in this equation using Hooke's law. Okay, next, the kinetic energy was computed here. The gravitational potential energy was computed here, along with the spring potential energy here. And entering the loop, these values were stored as the initial conditions, and the force of gravity and the force of the spring were calculated here, and the net force here. And using Newton's second law, we progressed the velocity and found the new position of the mass. And here we calculated the energy changes using the energy principle. And when you run this, okay, the red ball shows the observed motion and the blue ball shows the modeled motion, and they're pretty similar. And over here on the graph, the sum of the energies is the yellow line at 0, as we'd expect from the energy principle. The red and green oscillations are similar but opposite, and this makes sense because it's the spring potential energy and the gravitational energy. And the kinetic energy is in blue, and it also oscillates between negative and positive numbers, which makes sense because the spring stretches and compresses from its equilibrium points. And for your model system, is the principle satisfied? And it's yes, because there's no work done. The final work is the same as the initial, because the system contains the earth, spring, and the mass, so there is no outside interaction between the system and the surroundings, meaning delta E, which is equal to the work, is equal to 0, which is also shown here. Doesn't mean question. Using your data you obtained in Tracker, make 2 separate estimates for the oscillation period, one for the x position and one for the y position. And for this one, I did 3 oscillations, and so I did 3t, which is equal to the time 4.56, and I divided it by 3 to get 1.55 seconds. And over here I did the same thing, which was equal to 4.84 seconds, and I got 1.63 seconds. And they are relatively similar, meaning the time it takes to complete one oscillation for the x is equal to the time it takes to complete one oscillation for the y.